Morning all. What we're going to have a look at this morning are a few items on substations, and I want to talk about cable spiking. And what this is about, with 11 kV plus cables, they have to be proven to be dead. And the only way to do that really is to what we call spike the cable. And effectively what that involves is, there's your cable, you're going to fire a bullet using a special spiking gun, and I'll try and put a link on to solar to show you one in operation, but I can show you roughly how that works. We have a look at our piece of cable from last time. This is just the thickest cable I've got on offer at the moment. And what I've done is I've put a small voltage, 9 volts, on one end, and in reality, of course, it would be about 11 kV or 33 kV in your network. And I can prove by, I've got a screw here which simulates the bullet, and I'm just going to screw this in to the cable, and if the rehearsals prove well, let's see if I can get this in. As I going into a different hole there, it's going to the same hole I had last time. There we are. As I tighten this screw, you can hear it shorts out the cable. Now the idea is with cable spiking is that the cable is disconnected by usually a senior authorised person in your company, and they will then authorise you to spike the cable, because there's no real safe way of determining whether a cable is live or not from external testing. So the only way to prove it 100% is to fire a bullet into the cable and determine whether it's dead. So what you're proving is that it is actually dead, not live. In this situation, I've shown it's effectively live. But if I now disconnect the tester at one end and screw it in now, nothing happens. If the cable is live in reality, and the cable is charged to 11 kV or 33 kV, when you spike the gun there'll be an explosion, and it will cause a fuse to blow at the substation end, hopefully. Okay, so that's what cable spiking is about. It proves that the cable is dead, because it has to be disconnected first. Okay, right. We talked about tap changes the other day, and how they work. And there's your primary, and there's the secondary, and you've got an adjustable contact that moves up and down the secondary winding. Now, in practice, some kind of resistance has to be placed in series with this contact to prevent these windings actually short-circuiting each other. So there is what we call an impedance or a resistor in series. Prevents the windings short circuiting. Okay. Also, we remember from our, where's our transformer again? It's 11 kV, and this is the secondary, and we remember that the neutral is earthed. There's our neutral, there's our live. And sometimes, depending on the situation, from an engineering perspective, a resistor has to be put in the neutral to limit the amount of earth fault current that might occur in the event of a earth fault. So this is particularly important in a TNC situation where the neutral and earth is combined. So if you had a fault to earth, there's your, well, it's probably best just putting a fault down to earth there. You get a not large, very large inrush of current, and that has to be limited by this resistor in the neutral. So that is there to limit the earth fault current. Okay, that's that one. I might have to do 2 clips on this one. Yeah, I've only got a couple of minutes left, so here's our transformer again. And there's a washing machine. That's got earth metalwork on the outside. And if a live wire came off there and touched the metalwork, you're going to get a fault down to earth. And that's going to find its way back to earth here, because this is earth, remember, the start point. So the reason we earth metalwork, we call this metalwork exposed. Metalwork is earthed to prevent its voltage from getting high, i.e. it's actually got to be less than 50 volts. Okay, just going on to a second clip now because I'm running out of time on this one. See you in a minute.